And I thank the organizer for bringing us together. So actually the title is somewhat different from what the organizer had on their record, because I forgot what I have sent them before. Also, by looking at the title of the talks people did yesterday, I think a more appropriate title for my talk would be Mapping Materials and Molecules Made Fast. And before I ever start, I want to thank a very long list of collaborators: Norm, Garrett, Gabor, Volker, Edgar, Ryan, Christian, Hannes, Tomeo, Alex, Carsten, Tamash, Simon, and Bonan. Okay, so Max mentioned like I did my PhD in Michele Ceriotti's lab. And back then there was a trend in the lab for making these dimensionality reduction maps. And I remember back then it was Sandeep, who's the master of this. And he used to win all the poster prizes possible. So these are some example of the colorful maps. Oh, by the way, he also won all the Christmas card challenge. I think he made a firework out of these patterns. And back then, to be honest, I didn't quite understand what they were doing. And I also didn't understand how useful these things are. So they apply this to many systems as well. So apart from the all too familiar alanine dipeptide system, there's also carbon with amorphous carbon and many polymorphs, as well as the ice phases. This is work from Edgar. Now, so today, so here's how I'm going to entertain you for the next 30 minutes also. So I want to give you some idea of like how did I come to term with these colorful maps. And I will also, moreover, I want to introduce this ASAP code, which hopefully make the mapping task a little bit faster. And then I also want to justify a bit, like what is actually sort of the physical insights? What is the advantage for making these maps? Now, as far as I understood, like Rose has already gave some color on the dimensionality reduction. So I'll mostly like skip this part. And I just want to highlight the fact that Rose has introduced many methods like KPCA, MDS, and so on and so forth. And different methods really depends on this one question, right? So you have a bunch of high dimensionality data, and then you want to reduce the dimensionality into a low D data. And depending how your answer to this question, what exactly do you want to preserve, then you basically end up with a different methodology, which I will not go through. Okay, and another aspect of things is that how do we translate our physical chemical systems into this high dimensional input matrix. Now, typically we always start from the notion of atomic environments. So we have a system to start with that can be an extended system or it can be an isolated molecule. And then the first task is like we always divide the system into a set of atomic environments. And each atomic environment is basically like we're centered on one atom, and we have a sort of either a hard or a soft cutoff, and we cut off a trunk. And that is our atomic environment. And then we featureize these atomic environments. And then also for the global representation, we basically have to concatenate all the atomic environments into a global one. And then we can also do out many of the regression tasks based on the features of the atomic environment. The easiest, sort of the most common one is to fit an energy function. So we have atomic energy for each atomic environment. And this is basically the crucial step for many of the machine learning potentials. And there are also many popular representations to choose from, like the SOAP representation and the Taylor-Polynomial symmetry functions, and some other ones are amongst the most popular ones. Now, and why the notion of atomic environments is so crucial, particularly for the construction of the machine learning potential. So I would like to invite you to take a look at these two snapshots of atomistic system. And then I want to ask you, what do you observe from these two snapshots? And most people will be thinking, okay, the ones on the right is probably like a solid, and the one on the left is a liquid structure. The reason why you might be making this observation is because in a solid structure, all the atomic environments are rather similar. So in this case, it's like all FCC environment. But actually, if we look very closely, we can find repetitive atomic environments in the liquid as well. We can even find solid-like environments in the liquid. And I shall come back to this point a little bit later. This is, of course, we don't actually use naked eye to identify these environments, but instead rely on these representations that I mentioned before. And now, the reason why this is quite important to realize that there are repetitive atomic environments in our system. This is because this indicates that if we do ab initio molecular dynamics and we compute the energy and forces of everything again and over again, this is a very wasteful process. This is because we revisit similar atomic environments over and over again. And then if we take the nearsightedness argument, the energy and forces of each environment are like, or on the central atom are almost entirely determined by the environment, not so much affected by the atoms that are far away. This means that every time we encounter atomic environment, we can just simply sort of memorize what is this environment and what is the energy and forces associated with that environment. So next time when a new environment comes in, we can just make a comparison of the new environment with the ones in our memory and make a speedy prediction of the energy and forces of the new environment. So that summarizes the basic principle of constructing many of the machine learning potentials that are popular today. The first step is like we collect a bunch of atomic environments. And the next step is basically we make an interpolation, right? Of course, there are many open questions there. How do we collect these environments? And what is the optimal strategy? And also, how do we validate if our training set is complete, it covers what we want to cover. And once we construct the machine learning potential, and I'm sure Nong has mentioned this, and there are many advantages, including a very good scaling and low cost compared with the ab initio methods. And I want to mention that this atomic energy, which is so central to the machine learning potential, like I don't regard this as a physical quantity. It's more like a mathematical device. So to show this, so here I'm just showing you the atomic energy. So this is for water potential. So there's oxygen and hydrogen coming from two different fits of the machine learning potential. And you see they are not correlated at all. So, so although the global behavior of these two potentials are relatively similar, the atomic energy is not a physical quantity. And at first I was thinking, okay, so this is a water potential. I was thinking this is maybe due to the partition of the energy of the OH bond in each water molecule. So I was plotting out the water, the molecular energy of each water molecule, but there's still very little correlation between different fits of the machine learning potential. And then from all of this, I want to move on to go a little bit deeper about this representation of the atomic environment. So the idea is just that we need a similarity measurement. So if we look at these two atomic environments here, and which can be characterized by a list of displacement vectors of the neighboring atoms to the central atom. But if we just use this, then it's problematic, right? Because if you swap, let's say the index of two hydrogen atoms is still the same atomic environment, but the representation would change. So to conserve the rotation to permutation and as well as rotation and the translational variance, so the SOAP formula basically puts a Gaussian distribution on the center of each atom. So right now we have already translated this displacement vector representation into a density representation. And as you can see, this has already removed the permutational variance. And the next step is to remove the rotational variance. And to do that, we basically do an integral. We basically overlap the two density map. And then we do an integral of this overlap on all the possible orientation of rotation. So you can see after this, we also remove the rotational variance. And this guy is, of course, very hard to evaluate because if we have n atomic environment, to evaluate this overlap, we have to do n square operation, which is not ideal. But Albert and co-workers, they identify like indeed, we do not need to compute this overlap matrix explicitly, but instead we can expand all the density maps in terms of spherical harmonics. And then the density matrix, this kernel matrix, this kernel, the similarity between two environments can be returned in terms of using the coefficients of the spherical harmonics expansion. And so far we have talked about the atomic environment, and other times we are not just interested in the similarity between the environments, but also the similarity between two whole structures, right? It can be bulk structures or the similarity between two molecules. And in that case, we first need to transform the local representation into a global representation. And then the simplest way is to take an average. You can also take a sum or take whatever. And then from the global representation, then you can find the similarity between the structures A and B, which each contain many atomic environments. Okay, so and then to make all these tags as fast as soon as possible, so we developed this Python package called ASAP, and what this package does is that it first computes this atomic or global representations. And then it does some tasks such as mapping and specification and clustering and like symbol regression and so on and so forth. This is both a Python library, that offers an API, but it also, you can also use it as a bash command line tool. So when we use it after you install it, what you need to do is you simply type ASAP, generate descriptors, and then you tell it which descriptor you want to use. And typically these atomic descriptors have uses hyperparameters. So for SOAP, we use length scale hyperparameters and also the maximum spherical harmonics coefficients that you want to expand to and so on. But these are also determined, these hyperparameters can be determined automatically in ASAP. So this is what you need to type. and then you type another command to make use of the other functionality. So for example, mapping is like ASAP map and whatever file, and which descriptor to use and which dimensionality reduction algorithm you want to use, and so on and so forth. And then there's also cluster, kernel density estimation, sparsification, and so on. And the output, particularly after you make a map, the output can also be visualized interactively, both using a projection viewer developed by Simon or Chemiscope, developed by Gillon. That's how I would pronounce the name. Okay. So I'm going to show you some examples. So we started with this map made by Sandeep about alanine dipeptide, and we should come back to this example. So in the so like B, D, E are all like the maps produced use ASAP, and this is the actual commands that we used to produce this map. We didn't add anything else. So and I think it's quite telling to compare these automatic maps with the familiar Raman-Changin plot, because we know in Raman-Changin plot we usually represent the free energy of the system using the two dihedral angles, phi and psi, and this is what you get. And the Raman-Changin plot can tell us whether we have an alpha helix or beta folding or left-handed alpha helix. But the same thing can also be reviewed from our automatic map, made using just two Batch-learn commands. And also and one thing that is quite advantageous compared with the Raman-Changin plot is that when you use Raman-Changin plot, you always have to sort of break the periodicity, because like the dihedral angle goes from minus pi to pi, but you have to break the periodicity when you make the Raman-Changin map. But we don't have this problem with our automatic map. And the next example is for the QM9 dataset. So again, this is the exact command that we use to generate all these maps. And after you make this map, you can view this interactively. So these are generated from the projection viewer developed by Simon. So you can basically, after you made this map, you port it to the interactive viewer, and then you can click on each dot, which represent a molecule, and see what it actually is. And in this case, you can also color the map using different physical chemical properties, such as the band gap, the HOMO energy, and the number of, or like topological characters like number of rings or whatever. And basically the axis of the map strongly correlates with the type of the molecule and and also the morphology of these molecules. So coming back a little bit to this machine learning potential, like my experience is that this type of visualization is also very helpful for constructing as well as interpreting like the training sets of the machine learning potential. So one thing that I find, like speaking from my own experience when I started using machine learning potential, one exercise I find very useful is like I look at all the publicly available machine learning potential out there, and I want to sort of see what other people are doing that to make their potential usable. So here I just listed several openly sort of publicly available training set that I have made use of I have looked at over before. So and with the ASAP, again, using two commands, you can visualize what other people put in their training set. So for example, there's tungsten gap potential from Gabochani and co-workers. If you visualize it, it basically looks like this. And essentially what's happening is that they have some isolated atoms, some clusters and something like that. And that's pretty far on the map. And all the rest, these are probably interface, and then there are some bulk structures. And you can see clearly there are two stripes here. And especially if you use them like, you can also color them using like volume and energy, and there's a very strong trend of the change of the volume and energy. So I suspect essentially what they did is that they ran MD simulations at different density, like along like isotherm and isobar. That's probably what they did to compile this training set. There's also the a training set of boron from Volker Daringer. And then this is a little bit harder to interpret. So I'm coloring them according to volume first, and then energy. But still, it's very peculiar that you see there's a like, yeah, clearly like these stripes. And at first I didn't understand what's going on. But when I read the paper, apparently they were using random structure searches, which involve a geometry optimization. So these stripes are probably the last batch of structures that they obtain with a ground state energy, something like that. Okay, and a very primitive water potential that we have fitted a long time ago. And in this training set, we use two data sets. One is from the water simulation and the tripole point, and then the other is at the ambient condition, and you see two distinct patches. So I can go on and on, but this is the last example. And then for this training set that is from Tobias, so what they did is like for this water, they have a one patch correspond to liquid water structure. And then they also take like a few phases of solid ice, and then they were just doing the dilation of the simulation cell. So that's the sort of these line structures you see here are the ice phases, and this patch is a liquid water. Okay, and now I'm just going to go through two user case that I want to convince you that it's not just a sort of a gadget to beautify your paper, but this dimensionality reduction can actually bring a physical insights. So the first user example, when we were doing a random structure search. So this random structure search is a very simple method to predict the crystal structure. So the idea is very simple. You randomly throw a bunch of atoms in your box, and then you relax. In the end, you get various crystalline structures. But the problem there is that once you do that, you don't only get a few crystal structures, but you get like thousands of them. And it's very hard to interpret. You can use like space groups and whatever, but even different structures can have same space groups and so on. And now we were able to use this type of dimensionality reduction for like thousands of structures that we obtained from random structure searches. And then afterwards, we also did a clustering to identify the dominant patterns. And from these dominant patterns, we were able to identify promising candidates, and we were able to rediscover all the known polymorphs of titanium dioxide, as well as 15 other new polymorphs. So these were the polymorphs that we were able to rediscover, and then these are the new ones that actually have rather competitive enthalpy, at least at the level of the empirical potential that we use. As another example, this is an example on water, which we all know has it's very ubiquitous, but it also involves many unresolved mystery. So back then, what we did is like we fit a machine learning potential for water. This is again based on this simple formalism of like the total energy of the system can be expressed as the sum of the contribution of the atomic energy. And then, so back then we trained the potential using a bulk liquid water. It is 1,500 also structures in our training set. And now, again, to visualize the training set using ASAP, so we have a liquid water configuration, and 1,000 is from the classical MD simulations, and then the 5,000 also is from the path integral molecular dynamics simulations, which basically contains the nuclear quantum fluctuations. And you can see, although visually you wouldn't be able to tell the difference between the classical and the quantum mechanical water, this automatic map like identifies that. And so with this potential, we are actually able to predict pretty well the many properties of liquid water as well as ice. So for example, in this plot, I'm showing you the density isobar. So the dashed red line is the density of liquid water from the classical simulations. And then we have the liquid water from path integral molecular dynamics simulations, including nuclear quantum effects. So, and the green and the purple are for cubic ice and the hexagonal ice. So that's the two ambient pressure ice phases. So you can see in these, in all these cases, our theoretical prediction is just within a few percent of the experimental measurement, which are indicated by the stars. And moreover, the nuclear quantum, we also capture, like, let's say, thermal expansion coefficients of the ice phases, as well as the density maxima of liquid water fairly well. And we can also use this to do thermodynamics, and this is the typical workflow that we use. We use thermodynamic integration. We start from a harmonic reference, and then we do a first leg of integration to the classical system, and then to the quantum mechanical system. And bear in mind that the neural network potential, whatever machine learning potential that you use, it's not the reality, right? It's sort of an imitation of the reality. So there's always some small residue difference between your reference, your ground truth, and the machine learning potential. So typically we also add a correction term on top to bring it to the true ab initio level. And then we are able to predict the chemical potential difference between hexagonal ice and cubic ice. So as I mentioned before, we first compute the chemical potential difference at the classical level using the machine learning potential. And then, because otherwise, if we do it directly at initial level, would be not affordable. And then we corrected to DFT using this correction scheme, when we also add nuclear quantum effects. So here the message is that you see nuclear quantum effects significantly stabilize hexagonal ice and make it a little bit more stable than the cubic counterpart. And this explains why the snowflakes in nature we see are always the hexagonal ice, which have the sixfold symmetry. Okay, so coming back, and then the very perceptive of you guys have noticed that I trained the potential based just on liquid water, but I was using it to predict the property of cubic ice and hexagonal ice phases, which are not in the training set at all. So how is that possible? So we should come back to this dimensionality reduction to rationalize it. And moreover, we talk about hexagonal ice and and cubic ice, but indeed there are many more ice phases out there. So at the moment there are 20 experimentally confirmed ice phases, and there are many more that were hypothetical ones. So back then Edgar and co-workers did this work. They developed a scheme, and here they plot things using a sketch map. But you can also do this using PCA. You can also plot. So they start from a very large set of hypothetical ice structures, and they did some analysis and also to screen which are the promising ice candidates. But of course, like you don't have to use sketch map. In fact, like you can just use a PCA or KPCA without much noticeable loss of information. But okay, but the point here is that so we take the candidate promising ice candidates out there, which includes all the experimentally confirmed ice phases, plus more hypothetical ones. So that's 54 ice phases. Now, if we compare these 54 ice phases with liquid water configurations, we see that they are structurally different, which makes sense because they should be ice and water should be structurally different. However, the interesting things happens if we are not comparing, we are not making a PCA map of according to the global features, but we just compare the local, and we just compare the atomic environments. So in that case, you see like the atomic environments observed in the ice phases, which are these sparse red and the purple dots here. And if we compare them with the atomic environments in the liquid waters configurations, which are these light and dark blue here. I'm sure other people have more sophisticated way of describing these colors. You can see the environments in the liquid water phases. In the liquid water, almost completely covers the atomic environments that are pertinent to the ice phases. So this means that when we are constructing the machine learning potential and we only train on liquid water, but the potential has inadvertently seen these relevant environments for the ice phases and can thus give good predictions about these ice phases as well. So, so to confirm this, it is again because of the simple scheme of the machine learning potential. You do an interpolation of the collected atomic environments. So to confirm that this machine learning potential can indeed predict property of the ice phases, so we did some benchmark. So we show the comparison between the density predicted by the machine learning potential against the density predicted computed at the DFT level using different setup, FASP or CP2K, or as well as a different hybrid functional. And you can see in all the cases we consider like density, lattice energy, and the phonon density of states. The machine learning potential all give very good predictions. And this figure is a little bit hard to see, but we can zoom in and we can see for the ambient pressure ice phases, the high density one and low density ones, the machine learning potential always gave very good prediction on these vibrational properties. And because of the success of the machine learning potential in describing the ice phases, we can also make use of to predict the phase diagram. And again, we follow this scheme of thermodynamic integration. And then we computed the chemical potential of all the 54 ice phases. using the machine learning potential. At first, we were hoping that maybe we can discover a hypothetical phase size that is thermodynamically stable. But it just turns out the low free energy phases are all the experimentally confirmed ones. So that was a little bit disappointing. But then on the other hand, it also confirms the completeness of the experimental phase diagram of water. And then we take these phases of ice out, and then we do our usual thing. We correct it to the DFT level, and then we add nuclear quantum effects. So in the end, we are able to arrive at the first phase ab initio phase diagram of water. And moreover, it's computed at the different hybrid DFT levels, as well as considers nuclear quantum effects. Okay, and again, nuclear quantum effects have quite a pronounced role, mostly in shifting the phase boundary at the high pressure region. Okay, so with all of these, I would like to wrap up the presentation and just move on to the very brief hands-on tutorial. So again, this tutorial is around this code ASAP, and the fundamental principle for ASAP is that because personally, I do these tasks like mapping, like classification, and the sparsification over and over again. So I'm always wonder it would be like, I always want a tool that can shave off some time whenever I do this very frequent tasks. So I wonder how should we do it. So I'll first start sharing my screen. So are we supposed to move on to deep note? Is that the idea?
Yeah. Although maybe if there are questions, this might be a good time to take them. Just like one or two questions.
Yes.
So please raise your hand if you have them. If not, we can move on. Oh, okay. So Edgar raised a hand.
Yeah.
How surprising. Sorry.
I've got a track record at this point. Thanks first of all. Thanks, Bingqing. Of course, I'm familiar with some of it, but one thing that got me a bit curious, and I might have missed whether you already explained it or not, but you pointed out that the atoms per atom energies that you got from different neural networks trained on the same data looked very different. Did you have a plausibility kind of argument for this? I might have missed it.
But even when we think of the classical potential, right?
Mm-hmm.
And I think also Federico probably has some insights on this. So let's say if we take Lennard-Jones, which is a pairwise potential, no? So there it kind of makes sense if you divide energy half between two atoms. But why? You can also assign all the 70% of energy to one atom and
right.
30% to other. There's no reason why.
Right.
50-50, right? And when you think about three-body potential, it's even more complicated. How do you assign this energy? Right. So I think there's like the fact like the atomic energy are not the same. It's not the intrinsic to machine learning potential, but it's just a natural result of the fact like the atomic interaction is non-local.
Right. Okay. I think I can follow that argument. Yeah. Thank you.
I can follow it in the case where most of the energy is non-local, but still, like if you're fitting something that's a combination of a covalent term plus, something else, you'd expect it to learn a fairly consistent mapping, one would think, between the total energy and the, the partitioning into local environments. Otherwise, that suggests that our entire localization assumption is flawed, right?
But let's say if you have a water molecule, you have a OH bond, and let's say it doesn't break, right? So why do you assign 50-50 to oxygen and 1 to hydrogen? I can assign 70% to hydrogen and 30% to oxygen. You see, it's equally valid.
Sure. Well, I mean, but I would say for the same geometry, you can say, like, we assign 70% in this configuration and 50% in this configuration. It can be arbitrary, but I would expect it to learn the same thing. you know, what you showed was two different networks trained with different initialization parameters, I assume. And they had completely uncorrelated results. I'd expect at least some correlation.
I guess if I mean, following up on this, I suppose it's a question of how localized or delocalized, say, electron density as a measure, for example, is, right? So Bingqing's example with the oxygen-hydrogen covalent bond is a kind of a case where I suppose the localization is across the molecule more than on an individual atom. And so maybe if you summed up the contributions from the molecule, you'd arrive at a fairly consistent number across networks.
That's the next plot that you showed.
Sorry,
right? The next very next plot that she showed was the energy of a water molecule, right?
And that was, can we see that again, Bingqing? I think I missed it.
But there's actually no need to show it. It's just like they are not correlated.
Okay.
But my argument is that even if you have an empirical potential with 2-body and 3-body terms, there's no unique way to assign the atomic energy, right?
Yeah, at least for this, I wonder what. Yeah. I'm still trying to wrap my head around it. I suspect that, yeah.
Oh, but
I suspect you're right.
But that people can try them out themselves, right?
Yeah.
They fit 2 different fits of a neural network. Or you can even take the atomic energy from gap and compare that against the atomic energy from another machine.
Well, I would rather compare the atomic energy between different gaps versus between different neural networks, right? And I'm wondering if gap with its somewhat simpler structure in terms of the regularization and how it assigns the energies to atoms, maybe it's a bit more consistent. I don't know. That could be something to do in the future.
Maybe another, like the DFT way of looking at this could, I don't know whether I'm talking complete nonsense now, but I mean, if you think about allocating electrodensity to atomic centers, right, doing this kind of localization and association, you also have troubles because it's ambiguous.
Particularly for metals, right? You have,
even though they're different
electrons everywhere.
Then for sure, but even in systems that are fairly localized, you've got different ways of defining local orbitals and electron densities, which and different ones work well as far as I know. So there's no optimal solution. Maybe it's kind of a reflection of that in the neural network potentials, where you've got different local energies, but the total energies are well represented nonetheless. Okay, thank you.
It's an interesting question, but maybe we can move on to the tutorial for now.
Okay, so how do people should do it? Should I share my screen of the deep node, or people open their own deep node? Is that
both?
Okay. So I'll share my screen as well.
Yeah.
So I made this tutorial, and I believe what you can find them is in the main tutorial, and there's one like made by me. I have to admit, like I'm not a huge expert of using deep node, but essentially what one needs to do to make use of ASAP is that, so first we need to install it, so which can be installed using pip install. You can also, of course, download the it's public code, right? You can clone it from GitHub and do the setup install yourself. But okay, so let's say we do a pip install ASAP, and then it's installed. And then so I first want to show so you can use it as a command line tool. So for the command line tool, let's see. Is that supposed to, how do I run it? Run. Okay. So okay, it's a different key on Mac and on Ubuntu. Interesting. Okay, so it does wrong, but it takes a little bit longer compared with on laptop. So you can see if you just type it, and you can see the various options that it presents, including the first step is usually to generate the descriptors, and again they are various options. So let's see. So if we do a generate a descriptor help, and then tells you what kind of, again, what kinds of the options are there. So essentially, you have to find a way to pipe in your input file. And in our case, we're actually using an ASE parser. So any data format that can be used by ASE, we can also read. That includes extended XYZ, or if you use VASP or whatever, or CASTEP, these input files are all supported. And then you can also pick from different representations. So actually more implemented now, but essentially SOAP and atomic symmetry functions and some other ones. And same thing as the other ones. You can always type. You can just type to get some help. And so let's see if okay. How do I add a new? Okay, so this. Okay, so let's say to generate the descriptor. So basically, one type in generate descriptor, you pipe in the coordinate file. In this case, it's an extended XYZ file, and I specify SOAP descriptor, and yeah, you can also do this in parallel. It's trivially parallelized. And notice that for SOAP, typically one has to specify the hyperparameters, but these are actually automatically decided inside the ASAP. So ASAP can basically first look at what kind of elements are there and what are the characteristic bond length and so on. And then it automatically decides a good set of SOAP parameter. Okay, so now it's being computed. Yeah, it's here. Let's see if it works at all, but then you can do a map. So again, let's first do a helper string.
By the way, I don't know if the standard machines are parallelized, but if you want to use the Pro machine, which everyone should feel free to use because almost no one has, that's up to 4 CPUs.
I see. Okay, and then you can do a map. So again, you can first get the helper string. Oops. And then you pipe in the file that we just computed that contains the SOAP descriptor, and then it tells you which you can also specify which descriptor you want to use. In this case, I only have one there, so I can just put the wildcard. Sorry, and then you can specify which dimensionality reduction scheme that you want to use. So there's PCA and Tisney and UMAP and so on. I wonder if this works at all, because in the end, what will pop up is a image. So I wonder how this works.
Seems Daniel's raising a hand.
Okay, Daniel, you want to speak up?
Yes, thank you. Thank you for the talk. Thank you, everyone. I just have a question. I'm trying to look for more information about documentation, stuff like that, but I'm trying to search in Google and stuff like that, and ASAP, it's a fairly difficult term because there are a lot of things.
I think that's because, like, if you search AICP, surely like our little code wouldn't pop up. But there is a repo. Or maybe I'll send this in the chat.
Okay, thank you very much.
So there is a repo, and And as you can see, there's also a documentation. There's also a paper that describes it. So if you open up the documentation, I mean, it's not the best documentation in the world, but for scientific packages that people develop for fun and for with limited resources, this is as far as I can get. Okay, so back to this deep note. So you can see we basically we can make a plot, and eventually we made a figure. I don't know where do you get up. Maybe it's this one. Okay, so this is the figure that's being generated automatically, and there are some other more sophisticated options, and you can make the figure in a particular way and annotate it and color it using various things and so on. But this is the basic, but you can see how easy it is just using 2 commands, and you can already generate this PCA or whatever dimensionality reduction scheme you would like to use. Okay, so this is the command line tool, and in the last 2 minutes, I'll just very quickly go to like this Python API. So essentially, you can import ASCP as a library. And once you have imported as a library, and then you can, again, very simple procedure. You first initialize this AXCP XYZ class, and then we always use a dictionaries to specify which SOAP parameter you want to use. How do you go from the atomic descriptor to the global descriptor, and so on. And then finally, you just have to specify, you just have to pump the specification and compute the global descriptor. And there's also, you use another dictionary to specify which kind of a dimensionality reduction scheme you want to use. You can also use one after the other and so on. Same with the descriptors. You can have a hybrid descriptor that combines SOAP with different parameters, or SOAP with Coulomb matrix and so on. I just have to specify them. And finally, there's also the plotters in ASCP lib.plot. And there again, you use a dictionary to specify what kind of the specification you want. And then you just initialize a plotter object, and ta-da, you plot, and that's all done. Okay, so with that, I think I'm done.
All right. Well, thank you very much, Bingqing. Let's give her another round of applause. And yeah, so that's the end of this time slot. So we will start again at 10 past the hour. And yeah, so we'll have a little break and see you then.
Thank you.
Thank you.